We are talking about simple harmonic motion, which is motion that repeats itself. We were looking last time when we introduced this with examples like a pendulum that's swinging back and forth. We talked about doing it with a mass on a spring. It kind of sort of works with things that are moving in circles as well. And we know that we can express that motion as the amplitude of the motion times the cosine of omega t plus phi. And we talked about what all those things are. Like I said, xm is the amplitude, t is the time, whatever time we're trying to figure out the position for. Omega is the angular frequency, which relates to the regular frequency f and the period t. And then phi is the phase constant that basically shifts the cosine curve along so that we can use, well, it shifts the cosine function depending on when we let t be equal to 0, which again we talked about the other day. So we were working with checkpoint 1. And the first thing that we had to do was to come up with the equation of motion, which we did. And what was that? We used the initial conditions. We figured out what it was. It should be there in your notes. Plus what? No, we came up with a specific equation using the initial conditions that we solved for. Well, there's, yes, plus pi. Okay, we used the initial conditions and actually figured out what that phase constant had to be. Okay? And then we did part A. For part B, we want to know where the object is going to be when t is equal to what? Nope. That was for part A. Now we're on part B because we did part A yesterday. 3.5 times what? The period. That's capital T. Okay? So we could be clever about it because we know that every time we go through a period, it brings us back where? To where we started, which in this case was negative xm. So the first 3 periods of this time here are just going to bring us back to negative xm. And we could make a guess or a prediction that during that extra half a period, we would end up at positive xm. But we can check too. Now, we had to make a little bit of a modification to this formula in that we wanted to express omega in terms of the period or in terms of capital T. So what's that relationship between omega and the period? Again, it's in your notes from yesterday. Omega is equal to what? Yeah, is that right? Yes? Okay, so I can rewrite this as x of t is equal to xm cosine 2 pi over capital T times whatever my little t is plus pi. And then if I want to figure out where that object is for 3.5 periods, I'm going to have xm cosine. I've got 2 pi over capital T. And then I'm going to substitute in 3.5 capital T for my time. And I get something that looks like that. And of course, I can cancel my capital T's. And I get xm cosine 7 pi plus pi. Or xm times the cosine of 8 pi. And what's the cosine of 8 pi? 1. So as we predicted, we get xm. Okay. Everybody got what they need? Okay, so how about for part C? What time am I interested in for part C? 5.25 times the period. Where would you guess it would be after 5 1/4 periods? Okay, so that's what Zoe's prediction is. Anybody else have a prediction? All right, so again, we know that x of t is going to be xm cosine 2 pi over capital T times little t plus pi. Because all we're really doing here again is plugging and chugging. So x of 5.25 t is going to be xm cosine 2 pi over t times 5.25 capital T plus pi. Again, my capital T's cancel. So I get xm cosine 10.5 pi plus pi. Okay. And what's that going to be? What's the cosine of 11.5 pi? 0. All right. Okay. So, with all the other kinds of motion that we've encountered, we've always been able to not only have an expression for the position, but we've always had expressions for velocity and acceleration too. And we can do that for simple harmonic motion as well. So I have my generic formula here for a simple harmonic oscillator. And then how do I find V of t? How do I always find V of t? How can I always find V of t? Take the derivative of the position function. Okay, so xm is just a constant. It's the amplitude. So for whatever the system is, that's a fixed value. It's how far out I pull the pendulum. It's how far down I pull the spring. I could do it differently the next time, but for my system, that's a constant value. So how about the next thing? What's the derivative of cosine going to be? So I'm going to have negative sine omega t plus phi, but then what do I have to do? Multiply by the derivative of what's inside, which is in here, and what's that going to be? Omega. So my expression for V of t is negative omega xm sine omega t plus phi. Sometimes we call this the m, and then it would be the velocity amplitude. So how do I find a of t? Take the derivative of the velocity function. So again, I've got negative omega xm. Again, those are constants. The period of this system is a constant. This we'll find. What's the derivative of sine? Cosine omega t plus phi. But then I have to what? Bless you. Take the derivative of what's inside, which in this case will be omega. So I'm going to pick up another factor of omega here. And again, sometimes we let that omega squared xm be am, which would be the acceleration amplitude. Okay. But if you compare the acceleration equation with the original equation, what's this? It's x of t, right? So we can say that a of t is equal to, what is it, negative omega squared times x of t. Now, is a going to be a constant? No. Okay, so we're not going to be able to use our chapter 2 equations. But what equation involving a can I always apply? F net equals ma. Okay. So my a is going to be negative omega squared times x. Or f is equal to negative m omega squared x. The defining characteristic of simple harmonic motion, which means that it is not a simple harmonic oscillator if it does not obey this, okay, is that f is proportional to negative x. Not negative x squared, not negative something, not positive x. Okay. It's the force that's causing the oscillation, which would be the net force on the object. Okay. And I suppose we should put vector symbols on there because sometimes you'll see that the magnitude is proportional to x. Okay. What you might also see is that tau is proportional to theta, or tau is proportional to negative theta if we're dealing with vectors. Okay. Yes. Because if I had a pendulum, I would be dealing with an angle instead of a distance. You will also often see this as d2 dtx squared is equal to k times x, some random variable, some random constant, okay, that could be positive or negative. That would be simple harmonic motion. A very common question on the AP exam multiple choice is, which of the following equations describe simple harmonic motion? And they don't usually use F's and T's. They usually use the second derivative in the object, or the second derivative in the variable. So you need to have the second derivative, which is the acceleration, which is going to be proportional to the force, or the torque has to be proportional to the position, be it x or theta, to the first power. If there are vector symbols, it has to be negative. Because in all of these cases, the force associated with a simple harmonic oscillator is what we call a restoring force. Okay, which brings us to something really interesting. So let's hold on to this for a minute and take it to the next screen with us. So F is equal to negative m omega squared times x, the position. On one of the simple harmonic oscillators I showed you yesterday, we had a spring, right? Was the spring force? Well, negative kx. Okay, so if it's a spring force that's driving my motion, okay, then if I compare these two equations, what's k equal to? M omega squared. Okay. Which says that omega is the square root of k over m. Which tells me, and this is important and worthy of putting on a note card if you still have a note card, is that the period of my spring motion is only a function of the spring constant and the mass that I have on the end of the spring. It doesn't matter what the amplitude is. So whether I pull the spring down a little bit or whether I pull it down a lot, no matter what my amplitude is, it has to have the same period. Which is just kind of crazy. All right, so let's back up a little bit, and we're going to look at how x of t, v of t, and a of t kind of all interact here. Okay, so I'm just going to write them on the other board so that we can see them. So x of t is xm cosine omega t plus phi. V of t is negative xm omega sine omega t plus phi, and a of t is negative xm omega squared cosine omega t plus phi. And I think to make our lives easier, and what we're going to do right now, we're just going to assume that phi is equal to 0. Okay. And what I want to do is plot these quantities to kind of give you an idea of how they interact with each other. So I'm going to make 3 axes here that are all going to have the same time values. Okay, and so that's going to be 0. We're going to look at pi over 2. We're going to look at pi. We're going to look at 3 pi over 2. We're going to look at 2 pi. We're going to look at 5 pi over 2, and that'll probably be enough to give us what we need to know. Okay. So up here at the very top, I'm going to plot x of t. And as we've talked about, my object is going to fluctuate between xm and negative xm. Can't get any bigger, can't get any smaller. Okay? Everybody got the graphs? Almost. Okay. So, we'll do it this way. If t is equal to 0, what's x of t going to be? Not 0. What's the cosine of 0? 1. It's going to be xm. Okay. And in fact, we're not just going to plot time here, we're going to plot omega times time, just to make our lives simpler here. So if we let omega t be pi over 2, where's my object going to be? Zero. If I let omega t be pi, where's my object going to be? Negative xm. If I let omega t be 3 pi over 2, where am I going to be? Back at 0. If I let omega t be 2 pi, where am I going to be? xm. Okay, and I'll be back at 0 here. So I get a sine cosine function. Okay. Now we're going to plot v of t. And we're going to have the object go between Vm and negative Vm. Remember we talked about that, about the velocity amplitude, just because it makes our lives a little easier. So we're looking at the middle equation over there. If omega t is equal to 0, what's v of t? Zero. If we let omega t be pi over 2, so this is the sine of pi over 2, what's v of t going to be? Remember this. What's v? What's the sine of pi over 2? 1. It's going to be negative Vm. How about if omega t is pi? What's my velocity going to be? Shouldn't have to guess. You know what the sine of pi is. Okay. If omega t is 3 pi over 2, what's the sine of 3 pi over 2? Negative 1. I'm going to cancel with that negative 1, and I'm going to get what? Positive Vm. At 2 pi, where am I going to be? And at 5 pi over 2, where am I going to be? Negative Vm. So I get something that looks like that. Okay. Now we have acceleration. Again, I'm going to plot between AM and negative AM because I really just want the shape of the curve. So when omega t is equal to 0, what's the cosine of 0? 1. And so it's going to be negative AM because there's a negative sign out front. Okay. When omega t is pi over 2, what am I going to get? Cosine of pi over 2 is 0. When omega t is pi, what's the cosine of pi? Which is going to cancel with this negative 1 and give me AM. Oops, not there. Okay. When omega t is equal to 3 pi over 2, what am I going to get? 0. When I come back to 2 pi, what am I going to get? Or when I get to 2 pi, omega t negative AM, and then 5 pi over 2 is going to bring us back there. So we get something that looks like that. Okay. So let's kind of again think about the mass on a spring. Okay. So I start, how am I starting this? Am I pushing the mass up or pulling it down? I'm pushing it up because I have a positive amplitude, okay, or a positive position. What's it starting from? Rest. And then what happens to it? It accelerates down, which is what you would expect, right? You hold it up there and you let go and it goes down. Okay? So where does the spring or the simple harmonic oscillator have its biggest velocity or speed? When it's moving through the middle, when it's moving through equilibrium. Okay? Because here are our points. And you can see that its position is 0. What's its acceleration at that point? Also 0. So why does it keep moving? Well, it's moving already, right? Momentum. It's going to keep moving. How about what happens at the endpoint? When the spring is all the way down here at xm, what happens, or negative xm, excuse me, what happens to the velocity? Yeah, why does it have to go to 0? Why does the velocity go to 0 when I throw something up in the air and it gets to the top of its trip? Why does it have to stop? But why? Don't tell me it's because it's what the equations say. What does it have to do? It has to change direction. You can't change direction if you don't stop, if you're only moving in one dimension. So when I'm not going to throw this because this is the good pen, but when I throw the pen up, we've talked for months about how at the top of the trip, it comes to rest briefly because it has to change direction. And so that's the same thing here. When our object is at its extreme points, the velocity has to be 0. So the spring goes all the way down, it comes to rest so that it can change direction and start moving back up. Also note that the acceleration graph and the velocity graphs have opposite signs, which means that the acceleration or the force is always pulling towards the center, which is why we call it a restoring force, because that simple harmonic motion force is always pulling it back towards equilibrium. Okay? All right, we got it? We good? Okay. Um, we probably shouldn't. We should probably keep going, but I think we should stop because I don't think we're going to get through all of the problem and I don't want to stop in the middle.